Welcome back. Hope you're doing well. We're going to now discuss something a little bit different. So far, we've been discussing the linear geometry of things like Rn, and in particular, any finite dimensional vector space, how it looks a little bit like Rn once we start using these coordinate mappings. In particular, these things have algebraic identities between them. But there's more structure to Rn that we're familiar with beyond just the fact that there can be linear operators known as matrices that connect us to each of these other types of vector spaces. Rn has more structure to it than just that of a vector space. And we're going to be discussing that here in terms of Euclidean structure. Now, what do I mean by Euclidean structure? The Euclidean structure of Rn is defined by all of these other things that go beyond what we know as algebraic operations on this thing. And here are some examples of what those things can be. One of those is the notion of distance. The distance between 2 points. You have between two vectors of x and y, a notion of the distance that's given in between those two things. Now, even deeper than that, we have a notion of what is known as length. Right? If you have a vector x inside of Rn, you know what it means to talk about x and the length of it. The reason that I say this is a deeper notion than the notion of distance is that once I have a well-defined length, I can define distance in the following way. Just take the subtraction of these two vectors and take the length between them. That's the notion of distance. So when you talk about Euclidean structure, you're talking about these two things, distance and length. So that's what we're going to be trying to get into at this time, talking about these two particular notions and how Rn has a lot of structure beyond just the algebraic operations, the linear operations, I should say, for that it gets that any other vector space might have. So in addition to that linear structure, it carries the Euclidean structure. Namely, it has the length of a vector. It has even more than this, the angle between vectors, right? I can go through and calculate two vectors and have a well-defined notion of what it means to have an angle between them. And then finally, I can use that angle to help me calculate the dot product between two vectors. The dot product being the magnitude of x times the magnitude of y times the cosine of the angle between them. And that gives me the dot product of x dot y. So here you can see our picture that the way that we would write this and find this sort of dot product and how this sort of thing works kind of comes from some very interesting things. So for example, if I'm trying to formulate this picture here, if I want to figure out what this angle is, if I were trying to do this in trigonometry, for example, what I would do is I might start by trying to take a look at, okay, what is the cosine of this angle? What is the sine of this angle? Well, remember that the cosine of an angle, for example, is equal to x over r, right? R being the hypotenuse of the triangle. And of course, whenever we write these two things, we mean the lengths of these two triangles, of these two sides of the triangle. Here, for example, the hypotenuse length is going to be that of y. So that's something that we can expect, right? And then x, on the other hand, is something a little bit different. X isn't going to be the entire length of the vector x down here. It's only going to be a component of it, isn't it? So the question is, how do I go through and write that? Well, the way that I end up writing it is going to be in terms of x. Make sure that I'm saying this right. It's going to be in terms of the dot product, x dot y, like this, divided by the magnitude of x. And this is what is known as the scalar projection of y onto x. This is the scalar projection of y onto x. You may remember that this one has a little bit of a trickier formula to it, and that if you multiply this times the unit vector in the x direction, you get what is known as the vector projection of y onto x. But this is that sort of formula here. So if I go through and write this together and write everything down, then that's going to give me this definition of the dot product over here when I go through and solve for the dot product there. So this is the sort of picture that we have with the extra stuff, not necessarily talking about the linear operators here. In fact, everything here doesn't end up being addition or multiplication in any sort of vector space. Instead, you're bringing everything into the scalar field, into the real numbers before you start doing your operations. But this is additional structure beyond just the vectors themselves. Now, some properties of these lengths are very nice. In fact, we're going to see these vector lengths again very soon. So it's good to kind of keep in mind what these things are. I'm even going to be using these terms to try and talk about them. Positivity means that the length is always non-negative. Positivity, in fact, even implies that whenever it is zero, that only happens once, whenever your vector is zero itself, whenever x is actually zero. Homogeneity right, is this notion that kind of the magnitude you can take scalars outside of it, right? We're not going to say that the magnitude or the norm or the length operator, whatever we end up calling it, is going to be a scalar operator though, because even though scalars get to come outside, notice that there's a bit of a change. That magnitude has to have an absolute value by it. That magnitude has to have an absolute value to R. The reason being, of course, that's that whenever you take a magnitude of a vector, that's going to give me something less than or greater than or equal to 0. So if I had plugged in a negative number for R and didn't have these absolute values, I'd be straight out of luck. There would be no way for that to be equal. So I need these absolute values there. But that does restrict our ability to call this a linear operator. Another thing that restricts it from being a linear operator is the fact that it is not quite additive. It's something called subadditive. The magnitude of x plus y is less than or equal to the magnitude of x plus the magnitude of y. You may be familiar with this with another name, and the name that I will use as well, which is called triangle inequality. The reason that this is a triangle inequality, you can see right here, is that this is boiling down to the postulate that the sum of the sides of any two sides of a triangle cannot exceed the length of the third side. So for example, here and here, x and y, if I were to add these two lengths together, these two get from point A to point B indirectly, while this one gets there directly. So there's no way for this one to have a bigger length than these two combined. That's exactly the triangle inequality, right? So that's essential, the notion of some of the things about vector length, especially the properties that we want to be carrying with us in the future. So we'll keep these in mind together with their labels. Euclidean structure beyond this involves the dot product. So the dot product is also very interesting because it has a few other properties that look very much like how the length works after a little bit of a while. First things is that it also has positivity, that if you take the dot product of a vector with itself, it is also non-negative and only 0 whenever the vector is 0. Now, of course, this is only true whenever I'm thinking about the vector with itself. It is okay for the dot product to be negative. It is possible for x dot y to be less than 0. This is possible. However, if you're taking the dot product of an element with itself, that's always greater than or equal to 0. That's all that we need for positivity. Symmetry is one of the other ones. If you take the dot product of x and y, that's the same thing as the dot product of y and x. So that's what that one's called. Distributive law, if you have the addition of two vectors as one vector inside of your dot product, you can break up that vector into each of its terms and take a dot product of each one with z respectively, adding your results at the very end. Those two things will be equal. And finally, it has a notion of homogeneity that is in fact a little bit stronger. It actually is going to be linear in terms of either one of its variables. R can factor out of x in one of that variable there, or R could factor out of y in the same way. Either one is going to look very good for us. So this actually tells us that the dot product is linear in either variable, meaning in terms of x or in terms of y. Not in terms of like the whole thing, but if you think about how R factors in with one variable, that's how that works. So it's linear in each variable. It's not a linear operator, but it is linear in each variable. Now we can actually use the dot product to find some of this relationship between lengths and dot products. Namely, the magnitude of x is the square root of the dot product. It's the square root of x times x. And why is that? Well, think about how the magnitude formula is formed. Let's do this one in R3. Let's say that I have x1, x2, and x3. And let's say that I have, well, I just need the one vector for now. Let's say I have x1, x2, x3, like right here. Well, if I take the dot product of x1, x2, x3 with itself, then remember that the way the dot product works is, this is a neat trick for us to learn because we'll be using this a bit. Whenever I want to take this dot product, what I do is I multiply the x components, the y components, and the z components together. Once I'm done, I add all of my answers. So this is x of 1 squared plus x of 2 squared plus x of 3 squared. When I add all of those together, that's what I get. And notice that when I take the square root of this, what do I have? I have a distance formula. In particular, the distance squared equals x1 squared plus x2 squared plus x3 squared. This should look to you a little bit like the Pythagorean theorem. But the Pythagorean theorem works in 3 dimensions. It just has to have that extra component of your vector to it. We also have something like this. The dot product of x and y is equal to this quantity right here. 1/2 the magnitude of x squared plus the magnitude of y squared minus the magnitude of x minus y squared. Okay, where is this coming from? Let's think about this one for a little bit. So here we have the vector x. Let's draw that here. We have the vector y, vector right here. And then how would I draw x minus y in terms of in terms of how x minus y would look? Well, x minus y would look a little bit like this, right? So that it goes from the tail of one place to the tail of another. But how do I know what tail goes to what? Well, if this is x minus y, then I should be able to add these two vectors and get x, because you can see that the way that they're connected is like that. So y plus x minus y gives us the vector x. So this is how that sort of thing works. This dot product, remember, is very related to the cosine of the angle. In fact, we know that x dot y is the magnitude of x times the magnitude of y times the cosine of the angle between them. There's a little bit of law of cosines inside of here if you're familiar with this, but the reason that we get this is that we're looking at a triangle here where we can apply the law of cosines to this. And remember that the law of cosines can also tell us what the measure of this angle is inside of there. Just as a quick refresher, the law of cosines here would tell us that the magnitude of x minus y squared equals the magnitude of x squared plus the magnitude of y squared minus magnitude of x, magnitude of y, and the cosine of the angle between them. All right, so something like this. Oops, forgot my 2. That's what I was looking at. There's a 2 right here as well. By the way, if you go through and solve this for what this guy is, then that's exactly what you're going to get as far as your formula. So this can be rewritten and thought of as the law of cosines for this triangle here. So now we've discussed a little bit about some of this Euclidean structure. In general, let's take a look at Rn. We've been doing a lot of stuff just kind of without trying to deal with any of the individual components. Let's go ahead and calculate what these things are. Here is that formula for length that we were talking about before. Namely that the length of a vector inside of Rn is equal to the square root of v1 squared plus v2 squared plus all the way to vn squared. This is essentially a Pythagorean theorem type formula that works in general with triangles going in any direction. Lots of different triangles are being formed and showing that this vector works for Rn. The distance between vectors x and y is defined as magnitude or the length of y minus x. Notice the slight difference in how we kind of have talked about this length here. We've been using double bars here instead of everything else. So how is this different than the length that we were talking about up here? This is vector length. And in general, vector length is going to be something that happens in terms of abstract vector spaces. Abstract vector spaces can also have Euclidean structure, and we'll talk about that later on. But whenever we want to emphasize we're talking about things in the real numbers, we're going to be using these double bars instead. Notice that the double bars indeed have all of the length properties that we had talked about previously. The dot product is also given by this formula. Whenever I write the dot product here, I could be writing it in terms of x dot y. I could even be writing it in this form. Notice this. This is going to be a little bit tricky, and we're going to have to balance this notation as we move forward. That this sometimes means a vector if I have, for example, 2 scalars inside of here. But if I have 2 vectors inside instead, then then this is actually going to be a dot product. Or we'll have another name for this later on, and I'll update this name when we get there. So if I have scalars inside of my little brackets, it's going to be a vector. If I have vectors inside, that's going to be a dot product. Properties of the dot product are exactly like we want them to be. It is linear in each variable, and that name is going to be a bilinear function. See that it is both a linear function of x, that means in terms of the x variable here, and in terms of y. So that is a bilinear function there. We have the same relationships, what we've seen before, between lengths and dot products. And here's a new one that we haven't seen yet. Here is this one. This one's going to be that the absolute value of the magnitude of x and y is less than or equal to the magnitude of x times the magnitude of y. We're going to be calling this one the Cauchy-Schwarz inequality. This one's kind of interesting. Where does this one come from in terms of the real numbers? Well, think about what x dot y is, right? It's the magnitude of x times the magnitude of y times the cosine of the angle between them. And here we are taking a magnitude. So I'm going to be making sure that everything is non-negative. So I'm just going to take an absolute value of cosine of theta. Well, if we're talking in the real numbers, then these are all double lines right here. And this guy right here is the only thing that's left standing between this value and this value. But what do I know about the absolute value of cosine of theta? Cosine of theta is always in between 1 and -1. Because of this, I know that this is automatically going to be less than or equal to this guy. The magnitude of x times the magnitude of y. And that is the Cauchy-Schwarz inequality, at least in terms of the real numbers. We'll want to be talking about this in terms of abstract vector spaces as well. So this is something that we're going to keep in mind. So by the Cauchy-Schwarz inequality, for any non-zero vectors, we have this. In fact, this is really also just from the definition of dot product that we've been seeing before. Although Cauchy-Schwarz inequality has to get us there because we define dot product to not be quite magnitude of A times magnitude of B times cosine of the angle between them. We defined it to be the kind of more of a numerical property. So that's the reason why we have to say it's by the Cauchy-Schwarz inequality here. Here, theta is the angle between the two vectors, and we say that two vectors are orthogonal whenever the angle here is 90 degrees. Well, if the angle is 90 degrees, then we have cosine of 90 is 0. So we can also say that the dot product between those two vectors is 0. So let's go ahead and do this in a problem. Let's find the angle between two vectors. Let's find the angle between the vectors x equals 2, -1, and y equals 3, 1. To do this, I can either, okay, well, there's a couple of different answers. The easiest one that I can think of is instead of trying to find, just trying to, do like trigonometry stuff, is to use our formula that we've been seeing already. We have a way to take a dot product between these two with this formula, the multiplication of the x components plus the multiplication of the y components, all added together. So that should give us 2 times 3 plus -1 times 1. So that should get us 5. And then we have ways to find the magnitudes of each of these thanks to finding the distance. The distance of 2, -1 should be 5. And then the distance of 3, 1 should be square root of 10. Sorry, square root of 5 and square root of 10. My bad. So the cosine of the angle between them should be 5 over the square root of 50. Well, square root of 50 is 5 over square root of 5 square root of 2. So this is 1 over square root of 2. And so the angle between them is 45. Since 1 over square root of 2 can be rewritten as square root of 2 over 2. Now, we can also do this in terms of three-dimensional vectors. So we can go through and find the angle theta phi this time. This is a phi right here, between the vectors -2, 1, 3 and 4, 5, 1. Now, this one's going to be nice and straightforward. We could go through and calculate everything that we need to, dot product, magnitudes of the vectors, and use that formula to help us out. But this one ends up being very nice because if I take out and figure out what this dot product between the two vectors is, I'm going to get -2 times 4 plus 1 times 5 plus 3 times 1. And that's going to give me -8 plus 5 plus 3. That's going to give me 0 here. So the dot product between these is 0. Remember that we said whenever the dot product is 0, that's by definition orthogonal. The two vectors should be orthogonal to each other. So that means the angle between them is already known. The angle between them is 90 degrees. We could have been doing this not only in the real numbers, but in the complex numbers as well. But here it's going to be slightly different. How are we going to make this one different? Well, we want the complex numbers to retain the same sort of properties that we've been seeing before. Namely, if you take x dot x, we want this to be greater than or equal to 0. So x dot x, we want to be greater than or equal to 0. Now, there's an issue here if you have a complex number, because what if you had just the vector x equals like 0, 1? Remember that we've been talking about this in terms of R2. In terms of C, we might just call this I. Well, taking the dot product of I and I is going to give us -1, and -1 is not greater than 0. Because of this, we want to be very specific and say that whenever we take the dot product, the second component is going to have absolute value, is going to have conjugates over it. Let's talk about conjugates for just a second. We say that the conjugate of the number a plus bi is going to be equal to a minus bi. We're going to take explicitly the imaginary component of the number and replace b with -b. Notice what happens when I multiply these two things together now. If I multiply a plus bi times a minus bi, then what's going to happen is I'm going to be multiplying these things together. I'm going to get a squared minus abi plus abi, and then minus b squared I squared. Well, minus I squared, that's minus a -1. That's going to be positive there. And these two things are going to cancel out. This ends up being a squared plus b squared. Wow. In fact, a squared plus b squared actually retains a little bit of our notion of the length being the square root of the dot product. Because if I took the square root of this, I'd have a length formula for what this vector looks like. So this is going to allow us to help retain the complex vector Euclidean structure. But what we have to do for that is instead of using just the real numbers y1, y2, yn, we have to be using for the second vector the conjugates of each of y1, y2, and yn. So you can see here, this is exactly the formula that we had before. This gives us everything we need in terms of distance. So this gives all of the sorts of operations that we would like for the complex numbers, namely the dot product is 0 if and only if the vector x is 0, and the norm is defined as the square root of the dot product. So this gives us a notion of length in terms of the complex numbers as well. So just going to clear this up a little bit because I want it to be very clear here. Here we are thinking of the vector x inside of R2. Here we're thinking of the vector x inside of C1. Just wanted to kind of clear that up, make sure that was in case we come back to those notes later. But that's how we can talk about the Euclidean structure in both the real numbers and the complex numbers. Both of these are going to be very useful examples for us because as we move on to abstract vector spaces, we are going to want this structure in some of our vector spaces in the future. But that will do it for us today. Thank you so much. Have a wonderful day.